All right, hello everyone. Welcome to the bug finding and testing session. We have quite interesting talks in this session. And for the first talk, we have Dylan, and Dylan is going to talk about interesting Greybox fuzzing for concurrency testing. So take it away, Dylan.
Thanks. Yeah, so my name is Dylan, and I'll be presenting our work Greybox fuzzing for concurrency testing. So controlled concurrency testing is where we take a multi-threaded program and we serialize the execution. So we only allow one thread to execute at a time. And we also implement some sort of scheduling algorithm to decide which thread to run next after each event. An event here could just be like a memory load or store or any kind of operation in the program. So using the scheduling algorithm, we can explore many different possible orderings of the events in the program and hopefully find concurrency-related bugs. But unfortunately, there's exponentially many such interleavings, so we can't do this in a very naive way. We need a smarter search strategy. So to illustrate this point, I have a relatively simple motivating example here on the left. And in this case, the main function of this program is creating 100 setter threads and one checker thread. And the setter threads are just setting some global variables to be particular values. And then the checker thread is just checking the values of those global variables. And if the check passes, then there's an assertion failure, and we'll say that the bug is found for this synthetic example. So basically, we need at least one setter thread of the 100 to reach here in the program to trigger the bug, but none of the setters can assign a value to B, because that'll make the second part of the conditional fail there, and we won't see the bug. So if we take a very naive scheduling algorithm where we just pick a random thread after each event, in this case, maybe each instruction, we actually have a very low probability of finding this bug. And intuitively, this is because we have 100 setter threads that are all being created before the checker thread even gets started up. So the probability that we're not going to have at least one of them execute to completion is very, very low. But we can do better than just a completely naive approach. So there's been other prior work in this area. Maybe the most famous is PCT, which is a former ASPLOS submission. And PCT is focused on finding bugs with low depth. And depth here means the number of ordering constraints necessary to reproduce the bug. But unfortunately, again here, PCT does not work very well. The depth of this bug, according to PCT's definition, is actually very, very high. And the probabilistic bounds given by this algorithm are very poor for this large of a depth. So we need to do better. And if you look at this code again, it's not very complex. So it seems like we should be able to do better than what these algorithms are providing us. So we have a couple of observations that we're going to use as the basis for our approach for this work. And the first is to kind of reframe under what conditions this bug is triggered. And so really what we need to see is in the orange case that the checker thread is reading from the setter thread, and in the purple case that the checker thread is reading from the initial value of the variable B. And so these two constraints are really the reads from relation, or the reads from function, which maps each read in the program to the write that it observes. And so actually, if we frame the problem this way, there aren't so many reads and writes in the program, so it should be a little bit easier to find this bug. And in general, there can be exponentially fewer such read from relations in the program. So the second observation we have is actually not about the program, but it's about these algorithms that I talked about earlier. So I didn't go into too much detail, but these algorithms and a lot of the concurrency testing algorithms in prior work are completely stateless. So they don't reason at all about multiple executions. So every time PCT executes the program, it's like it's seeing the program for the very first time. And as you can imagine, if we add some state and persist information across executions, we should be able to do better than this stateless approach. So broadly, what we want to do with this work is find a stateful search algorithm that leverages the reads from relation. And this is where Greybox fuzzing comes in. So for those who aren't familiar, fuzzing has seen a lot of success in the domain of fuzzing open source applications for security vulnerabilities. generally not so much concurrent programs. But the basic approach is relatively straightforward. So if we were fuzzing like a PDF reader to find bugs, we might take some PDF files and randomly mutate them. So we flip some bits, and then we execute the program, our PDF reader, with these new inputs. And if we find a crash, great, we found some bug and we can report it, but usually we're not going to find a crash right away. So in fuzzing, you record some very lightweight instrumentation feedback from the execution to decide whether or not that execution exercised some new behavior that you haven't seen before. And typically this is in the form of code coverage. And if there's new code coverage, then that new input that you've generated gets put into the pool of inputs to be mutated further. And this way the fuzzing algorithm can prioritize inputs that have new behaviors while deprioritizing inputs that have behaviors that it's already seen before. And so the observation here is that this is exactly the kind of statefulness that we were looking for in our concurrency testing approach. So this allows the fuzzing algorithm to sort of learn in a very crude sense of the word about different executions and reason about multiple executions. So the question is how can we apply this kind of framework to concurrency testing? And to do this, we need to make a couple of changes. The first and most obvious is we're no longer operating on PDF files. So instead of mutating PDF files to generate new inputs to the program, we're going to mutate schedules to generate new schedules for the program. And I'll go into a bit more detail about what a schedule is in a future slide. The other change that we made to the Greybox fuzzing framework is to change the definition of what is a new behavior at runtime. So for input fuzzing, code coverage is a really great metric. But if we're fuzzing the space of schedules instead, you can imagine the code coverage probably isn't changing so much based on the schedule. So we need something a little bit more fine-grained in this setting. And this is where we start bringing in the reads formulation that I mentioned earlier. So this is a way that we can see that the multi-threaded program is exercising some new behavior, even if it hasn't reached a new coverage branch yet. All right, so I want to go into a little bit more detail on the schedule representation because this is pretty important to our approach. So what is a schedule? Maybe the most naive way you could represent a schedule is just a sequence of events that you want to occur in the program. So this is a schedule for the example program that I showed earlier, where we have the main thread start creating the other threads in the program, first the setter threads, then the checker thread. Then in this schedule, we have the setter threads executing first, doing all of the writes. And then at the very end, we have the checker threads doing the reads to each variable. And if we wanted to mutate a schedule like this, as we would in this fuzzing framework, we might reorder some of these events in our schedule. So instead of starting with the first setter thread, we might start with the last setter thread and then execute the checker thread and the rest of the setter threads. Or maybe we start with the 99th setter thread and then the 100th setter thread and then the rest of the operations. So we could do this, but there are a couple of problems. And the first is probably obvious from the slide. I'm running out of space here because these schedules can get very, very long. And for a real world program, you can imagine a schedule might have millions of events. So actually, even just storing a schedule in memory to be able to mutate it becomes an issue. The other, maybe more fundamental problem is that a lot of these mutations that we're making to the total order of events are essentially meaningless. So actually, these three schedules that I'm showing here have the same behavior in that program that I showed earlier. And that's because in each case, the reads on the checker thread are just observing the same values from the 100th setter thread in each case. So effectively, if we generated these three schedules, we've just done the same execution behavior 3 times, and this is a waste of resources. So to solve this problem in this work, we don't operate on the concrete schedule. We don't operate on the full list of operations that are occurring. We operate on abstract schedules. And again, here we're leaning on the reads from constraint. So This abstract schedule at the bottom says that the checker thread read of A should read from the setter thread write of A, and that the checker thread read of B should read from the initial value of B. And so any concrete schedule that satisfies these constraints, we would say instantiates our abstract schedule. And so this allows us to represent many concrete executions with just a single abstract schedule. We have a nice terse representation, so we don't have to worry about running out of memory or performance issues if we're trying to mutate a lot of these different schedules. And the added benefit is when we go to change these schedules via mutation, we're much more likely to get a semantically different execution as a result. So you can see if we were to change the first read from to read from the initial value of A instead of the setter thread value of A, we're very likely to get different behavior because it's reading from a completely different instruction in the program. So the data flow is completely different. So there's a secondary question. We have this abstract schedule, but we still need to run the program. So at the end of the day, we actually do need a concrete schedule. And to do this, we have a scheduler component that tries to fulfill or satisfy all of these reads from constraints at runtime. I don't have time to go into it in this talk, but I encourage you to check out our paper if that sounds interesting to you. So to summarize this work, we created a tool called reads from fuzzer. We're mutating these abstract schedules, enforcing them at runtime with a scheduler. And then after we've executed the program, we look and see which reads froms were actually satisfied and use that as feedback to guide the search going forwards. And this is all publicly available. So if you're interested, you can also take a look at the implementation on GitHub. For our evaluation, we compared with several other randomized concurrency testing algorithms, and we found that this approach does very, very well in comparison on a couple of widely used concurrency testing benchmarks. But maybe more interestingly, we looked at the state space exploration as a potential explanation for why our approach is so successful. And our theory was that RFF does well because it's exploring the space of reads froms evenly, or at least more evenly than other approaches. So we ran an experiment and compared with another concurrency testing algorithm, partial order sampling. We found that actually, yes, in fact, our approach does do a much more even exploration of the reads from space. So in summary, RFF is using Greybox fuzzing as a framework for concurrency testing and leveraging the reads from relation to do so. It's operating on abstract schedules and prioritizing new reads from behaviors via stateful feedback. It explores the space of reads from evenly, and that's what leads to good performance on the benchmarks in our evaluation. So I hope you'll check out our paper, and I guess at this point, I'll take some questions. Thanks.
Right, any questions?
Great work. I have a question about the validity of the scheduling that you are performing. Like, did you observe, whether some of the scheduling that you're applying there produces scheduling sequence, like a set of, write reads that will cause invalid sequence, so that using that sort of input is actually not a good idea and causes false positives maybe?
Yeah, so that's a good question. So that gets into a little bit of what I unfortunately couldn't fit into the talk. So the abstract schedules can definitely be infeasible, and they can even conflict with each other. Like you could say A reads from B and also A reads from C, and maybe those are conflicting. So that's what the scheduler component is trying to do, is it's trying to fulfill these constraints, but if it doesn't, we can still execute the program. And we're always executing the program according to some concrete schedules. So if we ever find a bug, it's not a false positive, it's a true positive.
Thank you.
Yeah.
Hi, Joe DiVietti, UPenn. Yeah, very interesting work. I was curious, in the reads from relation, is that defined over, program counters, like static instructions, or does it take into account the data flow? Because you could have, there could be multiple values that all flow through the same write or store instruction? And is there some way to explore that kind of space of different data values too?
Yeah. So for this work, we just use the static instruction. But there's different granularities that you could do it at. So you could do what you were describing. You could do like based on the actual value that you're observing. Like, did you even read a different value, even if it's coming from the same or a different instruction? So there's a lot of space to explore here, I think. But yeah, we just did one design point for this work.
All right, cool. Thank you.
Yeah.
All right, let's give another round of applause to our speaker. And with that, let's invite our next speaker, Zhenyang Dave. And he is actually not an author on this paper, so he's presenting for his friend. That's right. Yeah.
Yeah, that's
Yeah.
correct.
Cool. All right. So let's get.
Yeah, this one. Hey. Great. So, hello, I'm Zhenyang, not an author, but I'm presenting on behalf of Jia-Ju. So I'm very glad to introduce our work about fuzzing robotic programs. Robot operating system, namely ROS, is a very useful platform of developing robotic programs. It provides rich support for robotic program development, including many algorithms, libraries, sensor simulators, and so on. ROS has been widely used in various robot tasks like navigation and autopilot. Due to powerful functionalities, ROS is very popular now. ROS is used to develop hundreds of real-world robots and thousands of open-source projects. As robots can work in unknown environments like forests and factories, their bugs can cause accidents when interacting with humans and other robots. Thus, detecting ROS bugs is very important. Before detecting ROS bugs, we must know the properties of ROS programs. We will introduce three typical and important ones as follows. First, ROS programs can receive input from multiple dimensions, including user commands, configuration parameters, sensor messages, and so on. Second, a robot task requires multiple ROS programs to run together. Each ROS program's process is executed in a ROS node. For cooperation, these ROS nodes communicate with each other via message passing by a publish-subscribe mechanism. The figure shows typical nodes and their communication topics of a ROS navigation task. A robot task can explicitly or implicitly have some possible states, and these states are transformed between each other to handle different execution situations. The figure shows the simplified state machine of a ROS navigation task. To improve the security of robotic systems, several recent approaches have applied fuzzing to ROS programs. However, as shown in the table, these approaches still have some main limitations. First, these approaches consider just one single input dimension or randomly select mutated dimension for test case generation. Second, these approaches have no program feedback, or their feedback cannot generally reflect the state machine transitions. Finally, these approaches have weak generality and automation of testing different kinds of ROS programs. For example, they require manual work of writing ad hoc robot specifications. From these approaches, we summarize three main challenges of ROS fuzzing. First, how to generate multidimensional inputs in a proper way. Second, how to describe robot state transition using an effective metric. Finally, how to automatically test different kinds of ROS programs. To solve these challenges, we propose two novel techniques. For the first challenge, we propose a dimensional level mutation-based method, which generates multi-dimensional test cases by considering the contribution of each input dimension. For the second challenge, we propose a message-guided fuzzing approach, which extracts the feature of message between ROS nodes to guide fuzzing. For the third challenge, we designed these two techniques in generic and automated ways for different kinds of ROS programs. Let's see the first technique, namely dimension level mutation method. In our method, a test case has 4 parts, including user commands, configuration parameters, sensor messages, and sensor message order. Our method maintains a seed pool for each of these parts. In this way, it can clearly identify the contribution of each dimension's mutation to testing coverage. To select proper dimension from input mutation, our method validates the contribution of the current mutated dimension to testing coverage. If the contribution is large enough, our method still selects the current dimension for subsequent mutations. Otherwise, our method selects another dimension that is most infrequently mutated during fuzzing to perform subsequent mutations. For input mutation, our method just mutates the seed of only one selected dimension and select 3 seeds from the other dimensions to combine these 4 seeds into one test case. Let's see the second technique, namely message-guided fuzzing approach. This approach uses features of messages as program feedback to guide fuzzing process. Compared to code coverage and other coverage metrics, we believe message feature can more generally reflect the state transition of different robot tasks without code instrumentation. We collect message feature by identifying and combining the peak of message variation in each type. As shown in the figure, the message feature is represented as a 0-1 matrix, and it can clearly distinguish state transition in a robot navigation task. Based on the 2 techniques, we designed Rover, which is an effective fuzzing framework for ROS programs. It is independent from bug checkers and program languages and can support black box testing. So in our evaluation, we use Rover to test 13 robotic programs in ROS2, including 10 C++ and 3 Python programs. We also compare Rover to existing approaches. The evaluation, to existing approaches, sorry. The evaluation result shows that Rover covers more message features and finds more bugs than existing approaches. As for bug detection, it finds 88 bugs, including 45 new bugs that are never found before. 46 of these 88 bugs have been confirmed by ROS developers, including 26 new bugs. There's an example new bug in ROS2 navigation from official source. This bug is a use after free issue caused by threat concurrency. We also collect the contribution of input dimensions and show the result in the figure. We find that mutating sensor messages is most important to coverage improvement, and many found bugs are complex and involve 2 or more dimensions. Rover still have some limitations for future work. First, it focuses on detecting memory bugs and has no support for semantic bug detection. Second, it still misses some infrequent situations like error handling and concurrent executions. Finally, fuzzing efficiency can be further improved by using checkpoint or parallel processes. Let's make a conclusion. Testing ROS programs is important but challenging. We designed Rover to effectively fuzz ROS programs using 2 new techniques. In the evaluation, Rover finds 88 bugs in 13 common ROS2 programs, and it also outperforms existing approaches. Thank you for listening. Please contact the first author, Jia-Ju Bai, if you have any problems. Thank you so much.
So we have some time for questions. So authors should be available online. Are they? Do you
You
have any
mean
idea?
should the rover be available online?
Yeah, like on the Zoom call. Authors, if you're listening to me, can you unmute yourself for question and answer session? Let's see any participants.
I can choose between this one or a recording by the original author.
What do you mean? I'm seeing only one participant.
Hmm? I think there's no QA for the presentation.
Anyway, so we don't have authors available to answer any question answers for this talk. So we're gonna skip question answer for this session, this talk. All right, so we have our next speaker, Hunkar. Is that right?
Yeah.
Okay, over to you, Hunkar.
Thanks for the introduction. So hi, everyone. In this talk, I will introduce CSSTs, which is a generic data structure that can be used in concurrent execution analysis. So as we know, concurrency is hard and concurrency bugs are ubiquitous in practice. So bugs such as data races, deadlocks, dependency violations manifest very commonly. And a popular approach for finding concurrency bugs is dynamic analysis. So these techniques work by first running a program and observing an execution, and then performing a reasoning on this observed execution to check the presence of a bug. And there are widely adopted dynamic analysis tools in this context, for example, Sanitizer. And one very important aspect of these tools is performance. So the general setting of our work is concurrency and dynamic analysis. And I will start with a general picture of what we would like to achieve in this work. So assume we have a dynamic analysis that is trying to find some concurrency bug. And such analyses typically utilize certain existing data structures to maintain their state. So our aim in this work is to just replace these existing data structures with our new data structure CSSTs without really changing how the analyses work internally. And as a result of this change, the overall analysis becomes faster. So this is a general idea. So we can now look more closely at what happens underneath these dynamic analyses. So here we have an example of an observed execution from a dynamic analysis run. So we have 3 threads, and each thread contains a sequence of events. So these events can, for instance, be reading and writing to a memory location, as shown here, And to reason about the presence of a bug, a critical step in virtually all dynamic analysis for concurrency is to establish a causal ordering between the events of the execution. And causality is typically represented as a partial order. So for instance, edges in this figure represent the ordering relations that we have in this execution. So let's now see an example of how these orderings are actually added. So consider that we are now processing the third event of thread 0. An analysis could start by adding this edge number 1 that orders this event after its thread local predecessors. Then assume that this read observes the right of thread 1. In this case, we would add this edge 2. And adding this edge 2 results in certain inferred edges. So in this example, we would add this edge 3. And such inferred edges can be found by a process known as saturation, and it is widely used in dynamic analysis. So we can now actually make a distinction between the edges 1, 2, and 3. So in particular, we classify the edges 1 and 2 as edges that can be added easily into the partial order, because these edges are added onto the currently processed event, and they do not result in any transitive orderings in the partial order. However, in the case of edge 3, we can observe that the first event of thread 1 has many successors. So thus, in principle, this new ordering must be propagated along many events. So we would have to propagate this edge 3 like this. So what we can take away from here is that partial orders are essential for dynamic analysis. They are continuously queried and refined at each step of the analysis, and how they're actually maintained plays a crucial role for the overall performance of the analysis. And if you look at the current state of things, vector cloaks are a very widely used data structure in this context to maintain partial orders. However, in analyses where we have to insert these difficult types of edges, which happen widely in practice, the complexity of a single edge insertion is O of n, where n is the number of events. And the number of events can be very large in practice, which hinders performance. And on the other hand, vector cloaks support queries, constant time queries, and they do not support edge relations. So the main question that we ask in this work is, can we devise a new data structure with improved complexity for edge insertion, and which also supports edge relations? And to this end, we propose the CSSTs data structure. So the main difference between vector cloaks is that the O of n bound for edge insertion becomes roughly log n. But the downside is that the queries also become roughly log n. And initially, CSSTs support edge relations as well. And the complexities presented here are not very precise, and I will present the precise complexities later. But the takeaway message is that all these operations can be supported in roughly log n time with CSSTs. So I will now go into some of the high-level ideas as to how we achieved this result. So the general problem that we would like to solve is called dynamic reachability. And the input to this problem is a chain DAC. An example of a chain DAC is shown here. So essentially, we have a DAC that contains some chains, which are totally ordered, and there are some edges that go across these chains. And we are also given an online sequence of operations. So these operations can be inserting an edge or deleting an edge, which we refer to as updates. And we also have reachability, successor and predecessor queries. So these successor and predecessor queries answer the question of what is the latest successor or earliest predecessor of a node in a given chain. And the task is simply to answer queries correctly by considering all prior updates. So this is the general problem that we'd like to solve. We formulate the dynamic reachability problem as another classic problem known as dynamic suffix minima. So the input to this problem is an integer array A, and again, an online sequence of operations. So update operation simply updates the given index of the array with the given value, and we have min queries, which return the minimum value of the array in the suffix after the given index. So for example, consider the array A shown on the right, and if we perform a min query with index 1, this will find the minimum index of the array after the first index, and which is equal to 8 here. And we also have the arc minima queries, which I'm not going to detail, but the overall task is again the same as the task before. And segment trees are a standard data structure to solve the dynamic suffix minima problem. So a segment tree is essentially a binary tree. Each node in the tree has an associated range, and the value of each node represents the minimum value of the array in that range. And by using this data structure, it is possible to answer each update and query operation in dynamic suffix minima in log n time, where n is the size of the array. And dynamic reachability problem is formulated via dynamic suffix minima and in the following way. So for each pair of chains, we maintain an array like a T0, T1, and this array represents the reachability information from the chain T0 to T1. And the global reachability information is represented by the collection of arrays a T0, T1, T1, T0, and so on. And this is not a faithful representation of the underlying graph, but it is a faithful representation of all the reachability information in this graph. So here we see an example. The infinity entries in the arrays represent the fact that there are no outgoing edges. Race protection, where there are in these arrays, there are a lot of sort of sparse entries. And the reason is that now we don't only have related edges, but you also have some other edges, right? And then and we maintain sort of per chain, per pairs of chain, we maintain an array, right? And we can assume that maybe for particular pairs of chains, they may have some communication among them, then you may have some edges among them, but maybe some other chains do not have that much communication among them, and then you will not have that many edges. So in that case, this D will be very small.
Okay. One more question is, so it looks like all your queries, so even though you use segment trees and even though segment trees are meant for range minima, it looks like your queries are mostly of the form a comma infinity or minus infinity. Is that true?
Yeah.
Okay, so they're only one-sided ranges.
Yeah,
okay.
we only create the suffix of the array.
So, okay, all right. Yeah, thank you.
Yeah.
Any other questions?
Thank you for the nice talk. And your solution, to my understanding, your solution have worse complexity in query, right?
Yes.
And it is faster in updating.
Yes.
So does it mean that in the query is less frequent than updating in the real world application?
Can you repeat the question again? Sorry.
So does it mean that updating is more frequent than querying in the application?
It's not always the case, but for queries, we also have some other optimization that I did not talk about. So in queries, we also, in practice, we can also answer most queries almost in constant time. So we also have some experiments, scale-up experiments, where we compare the vector clocks with CSSTs. So we can see that for insertion, vector clocks are very bad compared to CSSTs. And for queries, vector clocks are better than CSSTs, but they're not far better. So they're still comparable.
Okay, I guess. Thank you.
All right. So I can ask one question. So how well your approach scales as the number of threads increases?
We generally assume that the number of threads is bounded. And so for instance, in this experiment, the number of threads is equal to 20. But typically we assume that the largest factor is the number of events.
Okay, so since you're maintaining some metadata per thread, right? So if I increase my number of threads to 40 or maybe 60, will I get better or worse performance than what you have with 20?
Yeah, the performance will degrade.
Okay, okay, cool. Thanks. All right, so with that, we have, let's give another round of applause for our speaker. So now we have last talk of this session, and we have our speaker, Shaohua Li.
Yeah.
All right, take it away, Shaohua.
Yeah, I think so. Whoops.
Is not working. This one? There's another doctor. Let me try this. Fix it. Let me try this. It's not okay. Okay. Hello everyone. My name is Shaohua Li. I'm a last year PhD student from ETH Zurich. Today I'm going to talk about a new framework we proposed to find the bugs in the sanitizer implementations. So sanitizers, they are widely used to detect various security bugs. For example, when using sanitizers in fuzzing, it has already, in OSS fuzz only, it has already found over 20K security vulnerabilities in popular open source projects. And popular sanitizers include address sanitizers for various security vulnerabilities, memory-related vulnerabilities such as buffer flow, or undefined behavior sanitizers such as UBFuzz for bugs like integer overflow, or memory sanitizers for undefined behavior, or MSM for undefined behavior like use of uninitialized memories. So how do sanitizers work? So suppose we have a program and this program is valid. So it's a perfectly valid program. So if you pass through the sanitizer on the right-hand side is a command line. So if you compile this code and run the final binary, so nothing reported, meaning that there's no undefined behavior detected by the sanitizers. However, if you use like a sanitizer to detect a program that contains contains undefined behavior, for example, here is a buffer overflow in the program. If you run the final binary, it will sanitizer will report a stack buffer flow in this case. So sanitizers are super important in detecting various undefined behaviors in the source programs. But what if for the second case, there's no report from the sanitizers, even if there's a undefined behavior in the input program? So in this case, we see that there's a false negative problem in the sanitizers, meaning that the sanitizer misreport some of the undefined behaviors in the source program. And in this work, we are targeting at automatically find and detect such problems in the sanitizers. Because sanitizers are so crucial, so now the question is, does the false negative problem really exist in sanitizers? So I'm raising this question because of the following fact. The first fact is that sanitizers are widely used in academia, in a lot of communities, like in the systems community, in the security community, in the software engineering community, and many more. The second fact is that sanitizers are widely deployed in industry. For example, in Google, Microsoft, and many more. These big techs, they are running thousands of machines every hour, every day on their internally. And the third fact is that there's no public research or public report that ever questioned the reliability or the robustness of sanitizers. And the last fact is that if you track the number of problems in the sanitizer bug trackers over the last decade, you can only find a few of them, and most of them, they are just usability problems, not about the reliability or the robustness problems of sanitizers. So all of these factors make it a general belief that sanitizers are reliable. They can reliably detect the undefined behaviors in our programs. However, in this research, we challenge this assumption. And after this work, you can see a substantially increasing number of reliability problems reported to sanitizers in their public bug trackers. So in one sentence that we propose the first validation framework for undefined behavior detectors. So in this work specifically, we constrain our scope to sanitizers because of their real-world impact. So at a high level, our solution works as follows. First of all, we generate a lot of programs that contains undefined behavior. For example, in this case, we generate the program that contains a buffer flow. Then we can verify if the sanitizer can detect this buffer flow or not. If it can detect it, then everything works, everything is okay. If not, we see that we potentially identify a false negative problem in the sanitizers. So the key to our framework now is how to generate this diverse kind of programs that contains all kinds of these undefined behaviors. Unfortunately, there's no available program generators that can achieve this goal, that is to generate various programs that contains undefined behaviors. So we design and implemented the first program generator that can deliberately generate all kinds of invalid programs that is a little bit deviate from the normal programs. So our work, so given a valid program, so our generator actually can be viewed as a mutator. That is, we work by given a valid program, then we introduce a bug pattern into the program to introduce all kinds of undefined behaviors. So in order to know how we design this bug pattern, we first need to know what makes a code well-formed in the context of C. Suppose for this code, this is a array index. So what does that mean for this code to be free of buffer flow? In this case, the well-formed code should satisfy the following condition. That is, array index should be within the valid range of the buffer pointed to by A. And for example, for the second code, if this bug pointer dereference is free of user free bug, that means the memory region pointed to by P is not freed at this point of usage. So in order to so our work is just to introduce mutations to deliberately break this well-formed condition for various code constructs. For example, to introduce buffer flow for the first code fragment, so we can just mutate the array index to make it access the valid range of the buffer A. For the second case, we can free the buffer range, buffer pointed by P before its usage. And in practice, we need to use both dynamic analysis and static analysis to get all kind of detailed information about the program. And here is just, and in our paper, we introduce all kinds of things, how we abstract the bug patterns at a high level to introduce such a bugs in general to the programs. And we did this kind of bug patterns for all popular undefined behaviors that's supported by the current sanitizers, like the buffer flow, user free, and integer flow, and so on. So at a high level, our work starts from a valid program generator. We take some existing valid program generator and we use this generator to generate a valid program. Then we introduce an analyzer to analyze the input program to provide the necessary information needed for our own generator. For example, in this program, suppose we can analyze that the array index K is constant and the size of the buffer A is 10. Then we pass this kind of information to the synthesizer, and synthesizer can then take use of this information to introduce the new programs that can break this like a well-formed condition in the input program. For example, in this case, we just mutate the array index and added different locations also to introduce various undefined behavior programs. And we call our project UBGen, the first ever program generator for generating this kind of programs contains all kinds of undefined behaviors. So now we can use, because we have this kind of a program generator, we can now use it to test the sanitizers. So we apply the UBGen to test the sanitizers, and we only use it for 1 hour. So the result is that in only 1 hour of testing, we got over 1,000 false negative reports from our tool. So does that mean our tool is super effective in identifying false negative problems? So unfortunately not. So let's take a look at a few examples. For example, in this program, this is a program generated by us. So on the left hand, in the top right, there's if you use the GCC-00 with the address sanitizer to detect the bugs in this program, so it successfully detected the buffer overflow. But if you use GCC-02 together with the address sanitizer, nothing reports. Unfortunately, this is not a sanitizer bug because the compilers, they have all kinds of optimizations. So what is truly happening is that the compiler, like GCC, they optimize this program to make it become a super simple program, such as like a return one directly. So in this case, there's no bug in the final program received by the sanitizer. So in this case, the missed reports is just by the aggressive compiler optimization. It's not a sanitizer bug. So there's an extensive discussion about whether or not this is something wrong with the sanitizer on VM. But the final conclusion from the developers is that no, they refuse to resolve this problem. Okay, so here's another problem. Another program generated by us again. In the last line of code, there's a buffer overflow D1A, which writes is overflow the write. So again, similarly, if you run with GCC-00, it can detect it, but if you run with GCC-02, it cannot again. Well, this is a sanitizer bug. It is not caused by the compiler optimization. So now the problem is that we need to differentiate the sanitizer bug from aggressive optimization. So aggressive optimization. So our solution to this problem is called, we name it as crash site mapping. So its motivation is from GDB debugging. Suppose on the left, this is a buggy program. This is the program contains a buffer overflow. So, and the sanitizer correctly reported. So if you run this program step by step, for example, you first execute the line 3, column 6, then you execute the line for column 3, line 4, column 5, and then you go into the address sanitizer region and report the bug. However, for the second case, that is you use optimized version, and if you check the final execution, you will see that nothing related to the overflowed buffer instruction in the final assembly code, and you can directly just return 1. That means this is caused by the aggressive optimization. So the intuition here is that the crash site, which can be viewed from the normally reported program, is not viewed in the final assembly, in the optimized assembly. But in the sanitizer, in the second case where this is a sanitizer bug, the crash site from the unoptimized version can still be observed in the optimized version. So we use this insight to differentiate these two cases. So, so our testing framework, we call it UBFuzz. It has 2 key components. The first one is the UBGen. It is used to generate various programs, contains all kinds of undefined behavior, and together with the test oracle, that is it's used to decide whether or not a missed report is really caused by a sanitizer bug or aggressive optimizations only. So the final result is that we use this like our approach to test the address sanitizer, UB sanitizer, and memory sanitizer in popular compilers, including both GCC and LVM. And then we reported over 30 bugs in the sanitizers, and most of them got confirmed by the developers, but only 6 of them got fixed in GCC. Roughly 10 actually right now, because this is shown in the paper, but later on in the last 2 months they fixed more. But our VM developer refused to fix any of them. Okay, that's just some like less maybe just LVM community, they're just too busy to fixing other bugs. So I would like to conclude my talk and ready for take questions. Thank you.
Thank you for the talk. And I have questions about whether the second solution can be used to find which optimizers are eliminating the undefined behavior. Yeah, because you have a debug information and you know in which optimizer it is appeared.
Thanks for the question. That's a nice question. So we didn't do this, but we can in principle do this. For example, in the optimization, you can just, for example, in the LVM, in GCC, maybe it's a bit hard, but in LVM, you can definitely do this. In the middle of optimization, you can just directly take the optimized IR out and use whatever, for example, LLC to produce the final assembly and use our this thing to track if whether or not the optimized version are still there, optimized the buggy instructions are still there. Basically, you can do that. Definitely do that.
Yeah, great work, very interesting. But I'm a bit interested in the impact of sanitizer bugs. So have you done any experiments on fuzzing with a buggy sanitizer and fuzzing with a good sanitizer? Is there any difference?
So thanks for the question. So if you still remember, in our first case, we said that so our initial, in this research, our initial goal is to stop right before our generator, that we find so many missed reports in sanitizers. So that's our initial goal. But later on, we find that and then we run the fuzzing with optimized version and unoptimized version. There are not a lot, but some real cases, real bugs, CVEs, that they are not discoverable in some of the compiler with optimized version, even with address sanitizers. But the compiler developers, they refuse to admit that this is their problem, because you have bugs in your program. So as a compiler, I'm free to optimize your code. Even if I'm optimized with the undefined behavior, the vulnerability from code, you should appreciate me, not blame me, okay? So then that motivates us to continue this research to the second case and try to differentiate them from that. So in this case, the compilers, they start to accept this as a buggy problem, as the buggy behavior in their compilers. But for the second case, whether or not they have the true impact, I have no answer to that.
Thank you.
Thank you.
All right, let's give another round of applause to our speaker. And I would like to thank you, all of you, to attend this session.